activity using tracking and clustering methods. Let's welcome Ms. Lan Xia.
Thank you. Good afternoon, everyone. My name is Lan. I'm from Helmholtz-Zentrum Gestalt in Germany. There are my colleagues Martin Zhang, Frank Faeser, and Hans-Wolf Storch who are also interested in this topic. And today I will talk something about a study of extratropical cyclone activity using tracking and clustering methods. Okay, in a warming global climate, the aspects of extratropical cyclone, such as the lifetime, numbers, or the distribution density are expected to be different. So that's why we want to do this work. We want to know how the climate change influence the activity of extratropical cyclones, especially on the northern hemisphere. But of course, you can do the same thing in southern hemisphere. And so we want to see how or what to influence from the climate change. And fortunately, we have model results, and model can tell you what happened before or what will happen in the future. I hope, at least. So we use a global climate model, which is called ECHO-G, and this model consists of atmospheric model and oceanic model. And we will use the mean sea level pressure fields and the data which is from 1000 to 1990. And the resolution of data is about 3.75 degree. And the model is proved can simulate the variabilities of pressure by other literatures. And then we will use tracking algorithm to track the cyclones or extratropical cyclones. I think my colleague gave you how to do tracking how to do track cyclone or polar lows. In my case, it's similar, but we use the tracking algorithm is from Heaven Cordius, which is developed very well and also designed specially for extratropical cyclones. And it's similar. First, we also will use filter to remove the background or large-scale systems. And then we will detect the minimum on mean sea level pressure and then connect the minimum to form tracks. So it's the same idea. And then we want to do clustering. We want to divide the tracks into different groups. So we use K-mean clustering method. So we want to say for each group, what's the change? So we can look at the frequency or distribution or the numbers change for each group. So that's how we do this work. And before clustering, every track is fitted into second polynomial function during the lifetime of this track. We did the same thing for longitude and latitude. So both parameters are for longitude and latitude. And the second zero order parameter will tell you the genesis locations. And the first order parameter will tell you how the direction of the track. And the second order parameters is about how the curve of these tracks. So every track can be described by these 6 parameters. And we will do the same thing for every track. And then we doing this clustering is actually clustering these parameters. And this idea is from Chu. He did also the same thing for tropical cyclones in Pacific. And just for validation reason, we compare our results with ReAND's data, just to make sure our data or our tracking algorithm did the right thing. So we can see this shows the density of cyclone genesis. That means the first point of the tracks. That means where the track begins. So this picture is from our model results, and this picture is from NCEP ReAND's data. And first, of course, we get the similar number from our simulation data, and also as this realist data. And we can see the density of cyclone genesis. For Pacific areas, the maximum of genesis is are located in Mongolia, northeast of China, around southwest China, near the Japan Sea, and in the center of Pacific. And actually, this work is consistent to other literatures. And for Atlantic areas, the genesis maximum are located in the lee of Rocky Mountain along the American coast, and also in near the Iceland. And this work also is accordance to Hawkins and Hodges' work, which is based on vorticity data. But of course, you can see the difference between two pictures, such as this part is stronger in realist data, and this part also. But generally, the patterns look not so bad, so that means our simulation data is not so bad, or our tracking algorithm did the right thing. But because it's climate global model, so it just gave the inertial data and changed the CO2. So of course, it will be some shift during this simulation. But generally, it's not so bad. And today, here I showed it's just the result of clustering. So I showed, unfortunately, we didn't finish all the work. So I just showed the winter time from 1900 to 1990. So I divided the tracks into 10 groups. But of course, you will ask me why I set down 10 groups. Actually, the clusters is very objective. So it's really dependent on you how much clusters you decide. So for my case, I decided 10 group, I think. Maybe I will show later it's reasonable. Such as class 1, this class 1 you can see is from the North Atlantic and will go into the Europe. And this one is beginning in the central Pacific. And such as this one, it also begin in the Caspian Sea. And I think this is corresponding to before result, the genesis errors. And these other 4 clusters. So you can see such as this one is from the Japan Sea or something and will go into the Pacific Sea. And this picture is showed all the centroids of all clusters. So it's all anti-clockwise. It's like this one, and actually it's also corresponding to the atmospheric circulation. And this is other people's also give this idea how this move of cyclones, and this is from Hawkins and Hodges and based on vorticity data, and also give the similar movement as my result, but the result is just experience core result and just gives the idea. Yeah. So my result is from clusters. And then you can see what's the numbers or average lifespan or the density of each clusters. So, and this is means the level pressure of this group. The numbers could be a little strange because it's after filter. But of course, the pressure is lower, means this group is much stronger. And the most, the largest clusters are class 2 and class 4. You can see this one. This one is, well, developed from the Baltic Sea and will go inside, and this one is from Pacific. And these two clusters are the largest one. And the fewest clusters are cluster 5 and cluster 7. That's what I showed. Cluster 5 is from, and we'll go to the and you also can look at the strongest one, are cluster 2 and cluster 5. They all developed on the ocean. Yeah, I think it makes sense. And unfortunately, you will see the strongest one are not the longest one. Usually you will see it's stronger and then it will longer. But it's really depend on where they go. You can see both of them are somehow will go on the land. So when they land or meet with the coastline, they will disappear quickly. So that means the lifespan also not so longer. So the weakest are class 5 and class 6 and class 8. You can see both of them are just developed on the land, so it's not so strong. And the longest ones are class 3 and class 10. Is as what I said, both of them are just developed. You can see they are not so stronger, but because they travel on the sea, and it's much easier to survive on the sea, and the sea will give them moistures or something, and they can survive longer. But if the tracks or cyclones will land, it will disappear quickly. Yeah, these tools are this number class 6 also the weakest and also the shortest. So yeah, it's because it's on the land, and usually the cyclones on the land is much weaker than the oceanic cyclones. And I'm not sure you can look clearly. Anyhow, this is time series of annual cyclone numbers for each clusters. Such as this cluster 1, you can see here the red lines are average number of this sub-period. You can see during this 1970s, the number is a little lower. Yeah, but for other clusters, there's no obvious trend. Yeah, but of course, just annual inter-annual variabilities, but not so strong trend during this 91 years. And this is time series for each cluster, but for the lifespan. Still, but some clusters are relatively survive longer, and some are shorter, but still not so obvious trend during this period. Anyhow, this is just preliminary work, just for we track and clustering winter storms from 1900 to 1990, using the ecology simulation result and with tracking algorithm from Highland Cordials, and the clustering method we use is K-mean. Anyhow, the spatial density of track genesis is similar as reanalysis data. And the oceanic cyclone is stronger, especially in the winter time. And the lifetime is really depend on the tracks are over the land or over the sea. And there's not obvious trend for numbers for lifespan for each clusters. But maybe we finish from 1000 to 1990, and then we can see what will happen. Yeah. Thank you very much.
You asked for 2 questions. I have a question. When you mentioned about cyclone, that is equal to hurricane, right? Or twist, because you said some cyclones generated from the Lan Xia.
Yes.
So is that equal to 1 twisting?
Hurricane could be included, but twister, it's too small scale.
Because you mentioned about Mongolia, I thought there's no sea there, but still
Yes, but there were some cyclones happened because of the topographic. There were big mountains and the wind from the mountain, and then they were curved because it's top mountains, because it's topographic.
Okay, thank you. Question?
Yes, I'm just curious about the last point of your conclusion summary. Do you feel disappointed because you don't see artist trends in your time series?
You mean there is no obvious trend?
Yeah, when you want to study something, you would like to see some trends. Right?
And yes, but it's just 91 years. Because what I want to do is from very long period. It's from 1000 to 1990. We just want to see nowadays and compared with very, very long time before. So in my case, the 91 years is just a very small period. So maybe it's fine, but I want to say compared very beginning and what's the difference from nowadays. Maybe one cluster will be very weak or one cluster is very high or something like that. So that's my idea. So I was a little disappointed with this. There's no obvious trend in this 91 years, but maybe look at the longer time, it's fine. Yeah, that's what I think.
Okay, any more questions? No. Thank you.
Thank you very much.
Okay, the next